Students of Chemical Engineering from Tecnológico de Monterrey, Campus Puebla, Gerardo Avendaño Hernández, Paulette Aguirre Rivera, and Luis Enrique Pedro Hernández Martinez are pleased to present the research project Photocatalytic Activity of Metal Organic Frameworks, Organic Dye Degradation of Congo Red.
Rapid globalization and urbanization had increased the demand for products made with dyes and heavy metals. The dye industry, which produced about 800 tons of synthetic dyes annually, relies heavily on synthetic pigments. The textile sector alone accounts for around 75% of the global dye market. However, poor dye fiction leads to water contamination through degrading effluents. Azo dyes, such as Congo Red, are rarely used and highly resistant to biodegradation, posing risks to aquatic life and human health. While various treatment methods exist, photocatalytics has gained attention for this, especially metal organic frameworks, particularly Mesoporous iron carboxylate, show strong potential as photocatalytics due to their semiconductor-like properties and high contaminant degradation efficiently. This project aims to sustainable synthesis Mesoporous iron carboxylate and test is available to degrade Congo Red.
As our methodology to synthesize Mesoporous iron 3 carboxylate under mild conditions, the procedure described by Sheng and co-workers was followed, making some small modifications. Using 6.49 grams of ferric chloride hexahydrate and 7.57 grams of trimesic acid were mixed with 300 milliliters of deionized water and charged into a 3-neck round bottom flask equipped with a digital thermometer, reflux condenser, and stirring shaft. The mixture was kept with a stirring speed of 300 revolutions per minute at 95 degrees using an oil bath for 12 hours. The reaction product was subjected to 3 purification cycles with ethanol and water and filtered using retention pore sizes of 2.5 micrometers and 25 micrometers, obtaining samples WM42 and WM4 respectively. Finally, the product was dried under vacuum at 150 degrees for 10 hours. For a particular photocatalytic test, 3 solutions of 200 milliliters of Congo Red at 25 parts per million were prepared. 134 milligrams of catalyst were added to 2 of the solutions. One of the mixtures was kept under white light irradiation for 220 minutes, while the other one was kept under darkness at the same time. The last solution served as a control and was kept under light irradiation in absence of MOF. Samples of 1.5 milliliters were withdrawn at several time intervals, centrifuged to remove any remaining MOF, and analyzed in a spectrophotometer in 498 nanometers. As a result, our current characterization techniques include Fourier transformed infrared spectroscopy, transmission electron microscopy, dynamic light scattering, and UV absorption spectroscopy. FTIR spectra indicated major peaks that confirmed Mesoporous iron 3 carboxylate was correctly synthesized. The variation in intensity and shape of the bands in both samples suggests a higher concentration of the functional groups and purity in the sample purified with retention pores of 2.5 micrometers. The TEM images obtained revealed that the synthesized method produces particles with a wide distribution of sizes and morphologies, with a tendency to agglomeration. A defined crystalline structure is not observed, which is common with many MOFs that do not require crystallizing agents for their synthesis. DLS results indicated greater particle size heterogeneity in sample WM4, with both samples showing low zeta potential, suggesting lower stability in suspensions as particles are prone to aggregation due to reduced electrostatic repulsion. With UV spectroscopy, the bandgap energies of both samples could be determined using the TOC equation, performing a TOC plot and extrapolating the linear region. Both materials show a high absorbance in the ultraviolet region and gradual decrease in the visible region.
According to characterization results discussed previously, it is concluded that the metal organic framework Mesoporous iron 3 carboxylate was successfully synthesized under mild conditions while keeping its core properties. The results of the photocatalytic test for the degradation of Congo Red indicate that the concentration of the dye in absence of MOF and exposed to visible light decreases slightly and remains relatively constant, with visible light having a minimal effect on its degradation. Approximately 7% of Congo Red was removed from this cycle. This slight downward trend could be due to photolysis. On the other hand, when MOF is added to the solution, the concentration decreases drastically in the first few minutes, suggesting a strong initial adsorption. After this decrement, the concentration fluctuates slightly, indicating a possible dynamic equilibrium between adsorption and desorption. However, unlike the sample that was kept in dark, from which 79% of Congo Red was removed, the concentration of the sample exposed to light tends to stabilize faster and at lower levels. 87% of Congo Red was removed at the end of the experiment. In addition to adsorption and desorption, a photocatalytic degradation of the dye occurs, which has been previously described in literature. The proposed mechanism, termed as adsorption-desorption degradation, ADD mechanism, is supported by comparing the dimensions of Congo Red with the micropores from 5 to 9 angstroms and mesocages from 25 to 29 angstroms of Mesoporous iron 3 carboxylate. This suggests that the dye can absorb within the MOF structures, but it could also desorb, causing the observed fluctuations. Then the degradation mechanism occurs. Mesoporous iron 3 carboxylate is excited by visible light, and an electron hole pair is on its surface is formed. After energy absorption, the electron is excited from the valence band to the conduction band, leaving a free hole in the valence band. Electrons then reduce the oxygen to oxygen radicals, which are then transformed to hydroxyl radicals. At the same time, holes oxidize the water molecules to more hydroxyl radicals that decompose organic dyes effectively. Thus, it is concluded that Mesoporous iron 3 carboxylate is viable for the degradation of Congo Red under visible light conditions, showing both adsorption capacity and photocatalytic activity.
We especially want to thank the Department of Sustainable Technologies and Civil Engineering, the Renewable Energies Laboratory, and the School of Science and Engineering of the Tecnológico de Monterrey Campus Puebla for accepting and supporting this project. We thank Professor Andrit Zavala and Dr. Pavel Cervantes for their valuable advice of the implementation and improvements to be applied to the project, and to Dr. Alma Cuellar for showing her constant support by providing facilities and information to carry out the project, as well as training for the special equipment. Finally, we thank Dr. Carlos Huerta for his dedication, excellent methodology, and teaching that he has shown as tutor and supervisor of the project.
Thanks for your attention. Harnessing light for cleaner waters and safer futures.